Imagine a region of space where gravity is so strong that nothing, not even light, can escape it. This is the essence of a black hole, an enigma that has captivated both scientists and dreamers alike. As we delve into this cosmic wonder, let's first explore how black holes come into existence. Black holes typically form from the remnants of massive stars. When a star exhausts its nuclear fuel, it undergoes a catastrophic collapse under its own gravity. In this moment, the core implodes, and if the mass is sufficient, it creates a black hole. This transformation marks one of the most violent events in the universe, a supernova. Historically, the concept of a black hole was first proposed by John Michel in 1783. He suggested that some stars might be so massive that their gravitational pull would prevent light from escaping. However, it was Albert Einstein's theory of general relativity in 1915 that provided the mathematical underpinning for black holes as we understand them today. Einstein's equations suggested that a sufficiently dense mass could warp the fabric of space and time, leading to the creation of a singularity. But there's more. A black hole is not just a void in space, it has an event horizon. This is the point of no return, where the escape velocity exceeds the speed of light. Once something crosses this threshold, it is lost to the universe forever. The size of a black hole can vary dramatically. Stellar black holes, which form from collapsing stars, typically range from 3 to several tens of solar masses. In contrast, supermassive black holes, found at the centers of galaxies, can weigh millions or even billions of times the mass of the Sun. For example, Sagittarius A*, the supermassive black hole at the center of our Milky Way, has a mass of about 4 million solar masses. Recent advancements in technology have allowed us to observe and study black holes more closely than ever before. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole, located in the galaxy M87. This groundbreaking image confirmed the existence of black holes in a way we had only theorized before. As we move forward in this exploration, one crucial question arises: what really happens inside a black hole? The truth may be more complex than we can currently understand. As we dive deeper into the next chapters, we will analyze existing theories, discuss the implications of quantum physics, and uncover what lies beyond the event horizon. But first, let's unravel the various types of black holes that exist in our universe, each revealing a unique aspect of these cosmic giants. As we venture further into this cosmic abyss, let's categorize the different types of black holes that exist. While they may all share certain characteristics, each type provides invaluable insight into the workings of the universe. The first type is the stellar black hole. As we discussed earlier, these form from the remnants of massive stars during supernova explosions. Their masses typically range from 3 to about 20 solar masses, although some can be even heavier. The process of formation can leave behind a swirling disk of matter known as an accretion disk, which emits intense radiation as material spirals inwards. Next, we have intermediate black holes. These are somewhat of a mystery. Although they are theorized to exist, few candidates have been conclusively identified. Their masses sit in the range of hundreds to thousands of solar masses. Scientists believe they may form from the merging of stellar black holes or through the collapse of massive clusters of stars. Their elusive nature makes them a tantalizing target for ongoing research. The most massive of all are the supermassive black holes, which rule the centers of galaxies. For instance, the aforementioned Sagittarius A* in our Milky Way, and M87 in the Virgo cluster. Their formation is not fully understood, but one prevailing theory suggests they grew by accreting massive amounts of gas and merging with other black holes. The sheer scale of these black holes raises profound questions about the evolution of galaxies themselves. Black holes serve not just as cosmic vacuum cleaners, but as crucial tools for understanding the fabric of spacetime. When observing their gravitational effects on surrounding stars and gas, we inadvertently gain insights into their true nature. For example, astronomers have tracked the orbits of stars close to Sagittarius A star. These observations have confirmed its mass and demonstrated the influence it exerts on the galactic structure. As we categorize black holes, we are drawn into the implications of their existence, namely, the concept of singularity. At the core of a black hole lies a singularity, an infinitely dense point where the laws of physics as we know them break down. This paradox invites a deeper inquiry into the fundamental laws governing our universe. What happens at this point? Can physics explain it? Theories of quantum gravity aim to bridge the gap between general relativity and quantum mechanics, posing potential explanations for what occurs in these extreme environments. As we delve deeper into the mysteries of black holes, we will explore these theories, particularly one of the most fascinating ideas, the holographic principle. But first, let's uncover what happens as we approach a black hole and the peculiar effects of its immense gravity. Imagine standing at the edge of a black hole, peering into the abyss, knowing that you are on the brink of unknown horrors and astonishing discoveries. As we journey toward a black hole, the environment transforms dramatically. A phenomenon known as spaghettification occurs, stretching objects into thin strands due to the extreme gravitational gradient. This effect is most pronounced as you near the event horizon. For instance, if an astronaut were to fall into a black hole headfirst, their feet would experience a stronger gravitational pull than their head would. The result? A stretching force that could tear them apart long before they reach the singularity. Beyond this terrifying transformation, nearing a black hole also leads to time dilation. According to Einstein's theory, time moves slower in stronger gravitational fields. As our hypothetical astronaut descends into the black hole, they would experience time at a different rate compared to an observer outside. A few minutes for the astronaut could translate to years for someone watching from afar. This realization brings the concept of time itself into question. As the astronaut approaches the event horizon, the effects of extreme gravitational forces come into sharp focus. Unable to escape, light itself becomes trapped in this region, creating the impenetrable boundary we call the event horizon. Beyond this point, we have no observational data, no light, no information can be retrieved. What lies beyond remains a profound mystery. Current theoretical models suggest that the laws of physics break down inside the event horizon. Theories such as the no-hair theorem state that black holes can be completely described by just three properties: mass, electric charge, and angular momentum. All other information, like the star's previous characteristics, becomes unreachable. This poses questions about information preservation, leading to the information paradox. One interesting perspective comes from physicist Stephen Hawking, who proposed that black holes can emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, suggests that black holes might not be entirely black after all. Instead, they could eventually evaporate over extraordinarily long timescales, losing mass and energy. Hawking's groundbreaking work opens a new chapter in our understanding, blending quantum mechanics and gravity, and invites us to ponder profound questions about the nature of reality. What does this mean for our comprehension of the universe? As we continue our journey, let's examine some real-life observations and experiments that lend credence to our understanding of black holes and their fascinating properties. As we journey through the enigmatic world of black holes, it's essential to look at the groundbreaking observations and discoveries that have shaped our understanding. Each breakthrough reveals more about these cosmic giants and their effects on the universe around them. The first direct detection of gravitational waves by LIGO in 2015 opened the floodgates for black hole research. These ripples in spacetime were caused by the merger of two black holes. This event provided direct evidence of black holes and a new way to observe them. By capturing these waves, astronomers can glean information about black hole masses, spins, and even the frequency of their mergers. The LIGO findings were monumental, confirming theories dating back to Einstein. The gravitational wave signal emitted during the merger was a game-changer, allowing scientists to observe black holes merging in real time, a feat only imagined in scientific literature until now. Furthermore, observations from space-based telescopes like the Hubble Space Telescope have been instrumental in identifying supermassive black holes at the centers of galaxies. For example, observations of the quasar 3C273 revealed a black hole with a mass over 1.5 billion solar masses. The Event Horizon Telescope's image of the black hole in M87 solidified our observational capabilities. This landmark moment not only provided visual confirmation but also illustrated the collaboration of various observatories around the world, linked by a network of telescopes that formed a planet-sized array. These discoveries fuel our understanding of galaxy formation and evolution. Supermassive black holes play a crucial role in regulating star formation across their host galaxies. The dynamics of gas accretion onto black holes, accompanied by outflows of energy, can regulate star production in the surrounding areas over cosmic timescales. As we analyze these findings, we dive into the complex interplay between black holes and the cosmos. But what does the future hold in terms of black hole research? With the advent of new technology and collaborative efforts among scientists globally, we can expect more discoveries that push the boundaries of our understanding. In the next chapter, we will explore the deeper implications of black holes, particularly how they challenge our concepts of spacetime, reality, and the fundamental laws of physics. As we pull back the curtain on black holes and delve deeper, we reach a realm that challenges our very perception of time and spacetime. The implications of black holes extend beyond just their existence; they touch the very fabric of how we understand the universe itself. In the vicinity of a black hole, the flow of time behaves strangely. While an observer far from the black hole experiences time normally, someone approaching the event horizon would perceive time differently. As they approach, they would find their time significantly dilated compared to someone watching from a distance. This peculiar effect raises profound questions. What is time? How do we perceive it? The distinction between past, present, and future becomes blurred in the gravitational embrace of a black hole. As you linger near the event horizon, time appears to slow. To an outside observer, it may seem as if the falling individual is frozen in place. This raises the question of how time may behave in other extreme environments across the cosmos. Theoreticians propose that the presence of a black hole warps not only time but the very structure of spacetime. According to general relativity, spacetime can curve around massive objects, creating a gravitational well. Near a black hole, this curvature becomes so extreme that the rules of physics as we understand them cease to apply. What happens within this curvature? Some physicists speculate that it may lead to alternate realities or timelessness, where the boundaries of our universe are tested. One area of research theorizes that black holes may act as gateways to other universes or dimensions; some might refer to them as wormholes. Although this remains speculative, it tantalizes our imaginations and opens doors to infinite possibilities. As we consider these concepts, we must confront the implications of singularity, a core aspect of black holes that raises questions about the limits of our understanding. If singularities represent points where our current laws of physics break down, how can we reconcile this with the quest for a unified theory that unites quantum mechanics and gravity? As we draw closer to the conclusion of this segment on the mysteries of black holes, we will reflect on efforts to resolve these questions through avenues such as string theory and quantum loop gravity. In our next chapter, we will focus on the paradoxes presented by black holes, particularly the information paradox, exploring how they challenge the very foundations of our understanding of reality. As we voyage deeper into the mysterious realm of black holes, we arrive at the heart of their intrigue, the singularity. This is the point where gravity squeezes matter into an infinitely dense state, something that pushes the boundaries of our understanding of physics. The singularity is theorized to exist at the very core of a black hole, surrounded by an event horizon, the boundary beyond which no light or information can escape. Imagine a gravitational force so intense that it warps spacetime to a degree we cannot fully comprehend. According to Albert Einstein's theory of general relativity, singularities are a natural consequence of the equations describing gravity. However, the laws of physics as we know them fail when it comes to singularities. The laws of quantum mechanics, which govern the behavior of particles at the smallest scales, seem to clash with the forces of gravity at these extraordinary densities. Recent research into quantum gravity seeks to bridge this divide. Scientists like Stephen Hawking suggested that the singularity could also involve something called Hawking radiation, a process through which black holes might emit radiation due to quantum effects near the event horizon. This means that black holes are not as eternal as once thought; they might eventually evaporate, leaving behind a trail of energy in their wake. The implications of understanding singularities are profound. If we can fully grasp these puzzles, we might uncover secrets about the birth of the universe itself. For instance, some theories propose that the singularities within black holes could lead to new universes, giving rise to the concept of a multiverse. This radical idea places black holes at the very heart of cosmic creation. But what does this mean for our understanding of space and time? When we look at these enigmatic entities, we're not just gazing into a void, we're standing at the frontier of knowledge, where reality blurs with the unknown. As we conclude this chapter, consider this: if black holes can birth new universes, what hidden mysteries await us beyond our observable cosmos? Our journey is far from over. While we may think of black holes as mere cosmic vacuum cleaners, their power extends far beyond just consuming matter. They are engines of energy and influence that shape galaxies and their evolution. Take, for instance, the supermassive black holes that are believed to reside at the centers of most galaxies, including our Milky Way. These black holes can be billions of times the mass of our Sun and can affect star formation, gas dynamics, and even the structure of galaxies themselves. Observations suggest that the energy emitted by accretion disks around these black holes, regions of superheated gas spiraling inward, can drive powerful jets of relativistic particles that shoot out into space at nearly the speed of light. The most famous of these phenomena is seen in quasars, which are incredibly bright and distant objects powered by supermassive black holes. When early astronomers stumbled upon quasars in the 1960s, they were puzzled. These objects emitted more light than entire galaxies. It's this light, formed by matter collapsing into the gravitational well of a black hole, that allows astronomers to investigate the universe's distant past. Interestingly, recent studies have explored the idea that black holes may play pivotal roles in regulating star formation in their host galaxies. The energy output from a black hole, as it devours matter and forms jets, may heat surrounding gas, preventing it from cooling enough to collapse into new stars. This delicate balance keeps galaxies from becoming too dense and might even regulate their growth. For example, observations of our own Milky Way's core suggest that the supermassive black hole, Sagittarius A*, may significantly influence the star formation rates of nearby regions. Could it be that these enigmatic entities are not merely devourers of material but also sculptors of the cosmic landscape? As we unfold the layers of black hole dynamics, we realize their influence extends far into the fabric of the universe. So, how do black holes manage to maintain such remarkable power? Ongoing research continues to reveal just how deep their impact runs, and the cosmos may hold even more secrets about their extraordinary abilities. As we conclude our exploration of what happens inside a black hole, the quest to discover and understand these fascinating objects is just beginning. Across the universe, astronomers are tirelessly working to identify not only more black holes but also to delve deeper into their complexities. The advent of advanced telescopes and observation techniques has revolutionized our ability to detect black holes, even those that are not actively consuming matter. One significant method is through gravitational wave detection. Since the first observation of gravitational waves by LIGO in 2015, we've confirmed the existence of numerous black hole mergers, events where two black holes spiral towards each other and collide, sending ripples through spacetime. This groundbreaking detection offers a novel avenue to explore black holes' properties and behaviors without directly observing them. For instance, scientists can infer their masses, spins, and even the dynamics of their collisions. Furthermore, upcoming telescopes like the James Webb Space Telescope are set to provide unprecedented insights into the early universe. With its advanced technology, Webb could unveil black holes formed shortly after the Big Bang, shedding light on the universe's evolutionary history. These observations may finally help us understand how supermassive black holes came to be and how they evolved alongside galaxies. As we venture further into this new era of astronomical discovery, the potential for new insights into black holes grows exponentially. What stories will the universe reveal to us next? Scientists propose that dark matter and dark energy, which compose most of the universe, might also have intersections with black hole physics. The relationship between these elusive components and black holes remains a tantalizing frontier in cosmology. With every observation, every discovery, we inch closer to understanding the deep-seated mysteries of these extraordinary cosmic phenomena. As we look to the stars, it's worth pondering, what else have we yet to uncover about the universe's most enigmatic entities? The hunt continues. As we unravel the intricate tapestry woven by black holes, we begin to see their profound implications for our understanding of reality itself. These celestial giants challenge our perceptions of space, time, and the fundamental laws of physics. When we consider what lies beyond the event horizon, we confront the possibility that our current models of physics might only scratch the surface of deeper truths lurking within the cosmos. Black holes create a unique laboratory for studying extreme conditions that are otherwise unattainable. Some physicists propose that by studying black holes, we can glean insights into theories that unite gravity with quantum mechanics, a so-called theory of everything. This ambition has driven many researchers, sparking intense debates and encouraging innovative ideas. For instance, the holographic principle suggests that all the information contained within a volume of space can be represented as a hologram on its boundary surface. This idea challenges our intuitions about dimensions and reality. Moreover, black holes may hold keys to understanding consciousness and our perception of reality. Some theorists argue that our experience of time and consciousness is intrinsically connected to deeper cosmic phenomena, such as the behavior of black holes. The intersection of neuroscience and cosmology may reveal connections between our understanding of the universe and our existence within it. The philosophical implications of black holes are profound. They challenge us to confront the nature of existence, the limits of knowledge, and the very fabric of reality. Consider this: if black holes can warp time, what does that mean for our understanding of destiny and choice? As we ponder these questions, we realize that black holes serve as a reminder that our universe is not just a collection of objects but a dynamic and interconnected web of relationships. The universe invites us to explore not only its depths but also the depths of our own understanding. As we wrap up this chapter, let's carry these reflections forward. How do black holes shape your understanding of existence? The answers may lie in the journey we take to explore the cosmos. As we conclude our odyssey through the enigma of black holes, we find ourselves contemplating the infinite mysteries that still await our discovery. Despite all that we've learned, black holes continue to baffle and intrigue us. From the moment we first theorized their existence to the current breakthroughs in gravitational wave detection and imaging, our understanding remains a work in progress. What lies beyond the event horizon? The question lingers, a testament to the limits of human understanding and the wonder of the cosmos. Each new discovery leads to more profound questions, reminding us that exploration is at the heart of scientific inquiry. The journey through these cosmic gateways teaches us not just about the universe, but also about our place within it. As we look ahead, the future of black hole research promises to be even more exciting. New instruments and technologies will continue to unlock the secrets of these astonishing objects. The potential for new insights fuels our curiosity, prompting us to ponder the ultimate fate of black holes, the universe, and even our own existence. Black holes force us to confront our limitations, urging us to push the boundaries of what we know. In this vast and mysterious universe, we must remain humble. The more we learn, the more we realize how little we truly understand. As we depart from the realm of black holes, let us carry forward the spirit of inquiry and wonder. We may have uncovered some secrets, but the universe harbors infinitely more. Each star, each galaxy, each black hole beckons us to explore further. As we close this chapter, remember, the quest for knowledge is unending. The universe stands ready to reveal its enigmas, and we are here to discover them. So, as we turn back towards the stars, let's hold on to our sense of wonder and curiosity. What will you discover next in the infinite expanse of the universe? Black holes are not just cosmic vacuum cleaners, they play a crucial role in the evolution of galaxies throughout the universe. It is believed that every galaxy harbors a supermassive black hole at its center, influencing the formation and distribution of stars in their vicinity. To understand this relationship, let's journey back to the dawn of galaxies. After the Big Bang, matter was distributed relatively evenly across space. But gravity began to shape these particles into structures. Some of these structures became the seeds for galaxies. As matter clumped together under gravity, some regions became denser than others, creating protogalaxies. And at the heart of these growing galaxies, black holes formed from the collapse of massive stars. These black holes, through their gravitational influence, pull in surrounding gas and dust, which contributes to star formation. The more massive the black hole, the more significant its influence on its host galaxy. One compelling example is the Milky Way. The supermassive black hole at its center, Sagittarius A*, has a mass of about 4 million times that of our Sun. Over time, it has shaped the orbits of stars around it, creating a dynamic environment where new stars begin to form while others are consumed by the black hole's immense gravity. This complex interplay highlights that black holes are not just destructive forces, they are also fertile grounds for the birth of new stars. Recent studies suggest that the gas accretion process on these black holes may drive galactic winds that can either promote or inhibit star formation in the surrounding areas. Galaxies grow in tandem with black holes. The feeding frenzy of black holes can illuminate vast regions of space, creating conditions under which new stars can emerge. The relationship between black holes and galaxy formation is further illustrated by the observations of quasars. Quasars are incredibly bright objects powered by supermassive black holes, and they provide us with a glimpse into the formation of galaxies billions of years ago. When we observe a quasar, we are looking into the past, often at a time when the universe was just a fraction of its current age. Quasars outshine entire galaxies, and their light, traveling across billions of light years, allows astronomers to study the conditions of the early universe. The discovery of the faint radiation emitted when gas spirals into a black hole reveals that these cosmic giants influence not just their immediate surroundings but also the entire structure of the universe. As we consider the link between black holes and galaxy formation, it's essential to appreciate the role of dark matter. Dark matter, which makes up about 27% of the universe, interacts with ordinary matter through gravity, shaping the clusters of galaxies and their formation. The gravitational pull of black holes, especially as they grow through mergers with other black holes and stars, may help create the conditions necessary for dark matter to influence the galaxy's structure. Astronomical surveys continue to probe these relationships, revealing that black holes might be a catalyst in the complex dance of matter across the cosmos. In conclusion, black holes are much more than cosmic oddities. They are essential architects of the universe. As we move forward in our understanding, we are faced with more questions than answers. What happens when two galaxies merge? How does the central black hole influence its galaxy over time? And how does this interplay continue to shape the cosmos? These mysteries remind us that the universe is a dynamic theater, constantly evolving, with black holes as its central players, and even greater discoveries await us beyond the edge of the event horizon. Stay with us as we dive deeper into the astonishing consequences of black holes on fundamental physics and the fabric of reality itself. Among the most mind-bending concepts related to black holes is the theory of Hawking radiation, proposed by the legendary physicist Stephen Hawking in 1974. This concept not only revolutionized our understanding of black holes but also blurred the lines between black holes and thermodynamics, presenting a paradox that has intrigued scientists for decades. According to Hawking, black holes are not completely black. They can emit radiation due to quantum effects near the event horizon. To grasp this, we must consider the environment just outside a black hole. The event horizon is the point of no return, where the gravitational pull becomes so strong that not even light can escape. However, quantum mechanics suggests that pairs of virtual particles are constantly popping into and out of existence throughout the universe. When such a pair forms near the event horizon, one particle can be captured by the black hole while the other escapes into space, resulting in what we now refer to as Hawking radiation. This luminosity implies that black holes can slowly lose mass over time, ultimately leading to their evaporation. Imagine a black hole emitting particles like a glowing ember. While it's a faint glow, the implications are profound. It suggests that black holes could eventually evaporate entirely, challenging the long-held belief that they are eternal. But the catch is that the emission of Hawking radiation is incredibly tiny, especially for larger black holes. For instance, a black hole with a mass equivalent to the Sun would take much longer than the current age of the universe to evaporate completely. However, smaller black holes, or primordial black holes possibly formed in the early universe, could evaporate much more quickly. This raises questions about the fate of these elusive, smaller black holes. Hawking's theory also asserts that this radiation carries away energy from the black hole, leading to a decrease in its mass. In a sense, they become thermodynamic objects, radiating heat like any other body. This notion introduces a conundrum known as the black hole information paradox. If a black hole can evaporate and eventually disappear, what happens to the information that fell into it? According to quantum mechanics, information cannot be destroyed, leading to heated debates among physicists. Can information be recovered from the radiation emitted, or is it lost forever? This paradox challenges our fundamental understanding of physics and the fabric of reality itself. The idea of Hawking radiation is supported by some indirect evidence, but direct observations remain elusive. Scientists have proposed various experiments, hoping to detect the faint glow of Hawking radiation from stellar mass black holes, but none have been successful so far. In recent years, researchers have turned to analog systems, using fluids or light to mimic the behavior of black holes to study Hawking radiation in a more controlled environment. One example is using lasers to create conditions that simulate the event horizon in nonlinear optical materials, creating a source of analog Hawking radiation. Through these experiments, we may glean insights into the enigmatic behavior of black holes and the fundamental nature of reality. As we contemplate Hawking radiation, we must confront the implications it has for our understanding of the universe. The balance between black holes that destroy and those that emit energy poses questions about the longevity of these cosmic giants and the fate of the universe itself. Will black holes evaporate completely, or will they morph into different entities? How does this interplay between energy and gravity shape the evolution of the cosmos? Hawking's contributions extend beyond black holes. His theories have led to advancements in our understanding of gravitational waves, cosmology, and quantum mechanics. It serves as a reminder that some of the most profound revelations in science stem from our efforts to understand the universe's most perplexing enigmas. As we continue to unravel the mysteries of Hawking radiation, we inch closer to grasping the fundamental principles governing the cosmos. But the question remains, what other astonishing discoveries lie beyond the horizon of our current understanding? We invite you to join us as we explore the frontier of black holes and their incredible implications for the fabric of reality. What if black holes are not just singularities that consume everything in their vicinity but gateways to entire other universes? This idea ventures into the realm of multiverse theory, a concept that has captured the imagination of physicists and cosmologists alike. Multiverse theory suggests that our universe is only one of many, each with its own unique properties and physical laws. Black holes could play a pivotal role in connecting these universes, acting as portals where matter and information could potentially pass through. Let's explore this tantalizing concept. The foundation of multiverse theory can be traced back to quantum mechanics and cosmic inflation. Quantum mechanics allows for numerous possibilities. A single particle can exist in multiple states until observed. In a similar vein, the inflationary model of the universe proposes that rapid expansion during the Big Bang may have created bubbles of spacetime, each evolving separately, resulting in distinct universes. Black holes, with their extreme gravitational forces and complex behaviors, could be the junctions between these universes. This notion leads to the idea of white holes, theoretical opposites of black holes that expel matter and energy. When a black hole forms in one universe, could it create a corresponding white hole in another universe, releasing the absorbed matter and perhaps leading to the creation of new galaxies or even new forms of life? Although white holes have yet to be observed, they remain a fascinating concept within the framework of the multiverse. One compelling hypothesis known as the wormhole theory proposes that black holes could be connected via wormholes, shortcuts through spacetime. If traversable wormholes exist, they might allow travel between different universes. Although still a hypothetical construct, this idea has driven countless scientific explorations and even inspired many works of science fiction. Imagine a spacecraft diving into a black hole, emerging in another universe, perhaps with entirely different laws of physics. Such scenarios ignite the imagination, but they also challenge our understanding of physics, as they require us to rethink space, time, and causality. While multiverse theory has gained traction, it's essential to address the criticisms surrounding it. Some argue that the idea of multiple universes, most of which are unobservable, lacks empirical evidence, raising questions about its scientific validity. However, proponents of the theory argue that the implications of black holes and the possibility of connecting to other universes offer valuable insights into the fundamental nature of reality. It forces scientists to confront the mysteries of existence, pushing boundaries and encouraging further exploration into the cosmos. As we investigate the potential links between black holes and the multiverse, we also encounter the concept of information preservation. The fundamental question remains, if a black hole connects to another universe, does information still exist after entering? The implications for quantum mechanics and the nature of reality are staggering, challenging everything we think we know. Scientists such as Juan Meldacena have proposed theories where information can emerge in a different form in a parallel universe after being swallowed by a black hole. This could offer a resolution to the black hole information paradox, providing insights into how information could be preserved across universes. As we mull over the mind-bending implications of black holes and the multiverse theory, we are left with more questions than answers. What does the existence of multiple universes mean for our understanding of life, reality, and the cosmos? Are we merely one universe among countless others, each with its own unique destinies? As we unearth these connections, the universe reveals its enigmatic nature, prompting us to ponder our place within the vast tapestry of existence. In the next chapter, we will delve deeper into the ever-evolving landscape of cosmic exploration and understanding, where black holes continue to captivate our curiosity and imagination. Black holes have fascinated scientists and laypeople alike for decades, yet they remain one of the most perplexing phenomena in our universe. The paradox of black holes arises from the very nature of their existence. When matter crosses the event horizon, it seems to vanish from our universe, disappearing into a realm where conventional physics falls apart. This peculiar behavior leads to questions that challenge our understanding of the cosmos. What happens to information that falls into a black hole? Is it lost forever, or does it somehow escape? This dilemma, known as the black hole information paradox, was famously highlighted by physicists Stephen Hawking and Kip Thorne, both of whom contributed significantly to our understanding of these enigmatic entities. In the 1970s, Hawking proposed that black holes are not completely black but emit radiation due to quantum effects near the event horizon, now termed Hawking radiation. This discovery initiated a series of debates surrounding the fate of information in black holes. If black holes can emit radiation, does this mean that the information that fell in can be retrieved? However, if it does, it contradicts a fundamental principle of quantum mechanics known as unitarity, which dictates that information cannot be destroyed. To illustrate this paradox, consider the case of a hypothetical black hole formed from a star. As the star collapses, it pulls everything in, including any information encoded in particles. Hawking's work suggests that when black holes evaporate, the information captured is either destroyed or encoded in the radiation itself, leading to possibilities that seem contradictory and perplexing. Recent theories, like the holographic principle, provide intriguing insights, suggesting that all the information contained within a volume of space can be represented as a two-dimensional information on the boundary of that region. As we delve deeper into this paradox, the implications stretch far beyond black holes themselves, potentially reshaping our understanding of physics. The quest to solve the black hole information paradox invites us to explore the limits of human understanding and the unknown aspects of our universe, leading us to a profound realization: the universe has secrets yet to be unveiled. Can we ever truly comprehend what happens in a black hole, or will it forever elude our grasp? As we conclude this chapter, one must wonder if the answers lie at the precipice of our knowledge, waiting for brave minds to explore these forbidden realms. The event horizon, often referred to as the point of no return, marks the boundary around a black hole where escape velocity exceeds the speed of light. Once an object crosses this boundary, there is no way back, which heightens the fascination surrounding black holes. But what really happens at the event horizon? To understand this, we first need to grasp the concept of spacetime. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime, creating the gravitational pull we associate with black holes. When crossing the event horizon, the laws of physics as we know them begin to unravel. Consider this: an astronaut falling into a black hole would experience a phenomenon called spaghettification. As they approach the event horizon, the gravitational forces acting on their feet would be so much stronger than those on their head, stretching them into a long, thin shape, much like spaghetti. This gruesome fate is a result of the extreme tidal forces generated by the black hole's intense gravitational field. However, from the perspective of the astronaut, their experience would be drastically different. They wouldn't notice anything strange at the moment of crossing. Time would appear normal. This leads us to ponder how time behaves in these extreme realms. As one falls deeper into the black hole, they would witness the universe outside speeding up, as time slows down for them due to the effects of gravity on time perception. This paradoxical experience illustrates the mind-bending nature of black holes. Furthermore, the event horizon acts as a shield, where information remains hidden from the outside world. But does this mean it is lost? Recent studies suggest that perhaps, through entanglement and other quantum phenomena, information may find a way to escape, forever changing our understanding of this critical boundary. As we continue to explore the implications of the event horizon, one must wonder, what secrets lie beyond it? What mysteries of the universe remain locked away in the gravitational grip of black holes? The answers might just reshape our reality as we know it, creating more questions than they solve. From science fiction films to best-selling novels, black holes have captured the imagination of artists, filmmakers, and writers for generations. Their mysterious nature and the frightening prospect of their existence fascinate us, prompting creative explorations that push the boundaries of storytelling. In popular culture, black holes often appear as gateways to other dimensions or time travel portals, enabling characters to traverse space and time in thrilling narratives. Films like Interstellar, directed by Christopher Nolan, brought black holes into mainstream consciousness, showcasing realistic depictions grounded in scientific theory. The film's portrayal of the black hole gargantua was so meticulously crafted that it attracted the attention of physicists, including Kip Thorne, who served as one of the film's executive producers. Being involved in the project allowed Thorne to ensure that the depiction of gravitational effects, time dilation, and the physics surrounding black holes adhered closely to contemporary scientific understanding. This collaboration between science and film demonstrates how black holes can serve as a bridge between complex theories and accessible storytelling. In literature, we find numerous examples of black holes being used as narrative devices. For instance, in the novel The Three-Body Problem by Liu Cixin, black holes are intertwined with themes of civilization and survival, pushing the reader to grapple with existential questions about humanity's place in the cosmos. Furthermore, black holes have been a topic in various television series, like Doctor Who and Star Trek, where they are depicted as challenges to be faced and understood. As audiences engage with these stories, they often find themselves drawn to the drama and mystery, igniting a desire to learn more about real-life black hole science. This interplay between science and popular culture not only enriches our understanding of black holes but also highlights the impact of storytelling on public interest in science. As we journey through the captivating narratives of black holes, we must consider, what influence do these portrayals have on our perception and appreciation of the real universe? The line between fiction and reality may be thinner than we think, fueling our curiosity and expanding our thirst for knowledge. The very concept of a black hole raises intriguing philosophical questions about information and reality. At the heart of these discussions lies the black hole information paradox, a puzzle that has baffled physicists for decades. What happens to the information that enters a black hole? Is it lost forever, or does it somehow escape? Let's delve deep into this paradox, starting with the foundations of quantum mechanics. In the early 1970s, Stephen Hawking proposed that black holes might not be entirely black after all. His groundbreaking theory suggested that black holes could emit radiation, now known as Hawking radiation, leading to the slow evaporation of black holes over astronomical timescales. This idea raised further questions. If black holes can evaporate, what happens to the information about the particles that fell into them? According to classical physics, information cannot simply vanish from the universe. Yet, as a black hole evaporates, the encoded information of the matter it consumed seems to disappear. This contradiction is at the heart of the information paradox. As physicists grappled with these conundrums, different schools of thought emerged. some suggested that information could be preserved in a holographic manner at the event horizon, the boundary surrounding the black hole. Others contended that the information might somehow escape the gravitational grasp of the black hole during its evaporation process. These theories have prompted extensive research and debate within the scientific community, leading to innovative breakthroughs. In 2015, a team of researchers proposed a new framework known as erasure to explain the resolution of the paradox, suggesting that lost information could be stored in the event horizon itself. However, as of now, no consensus has been reached. This ongoing quest to solve the black hole information paradox not only challenges our understanding of physics, but it also pushes the boundaries of our knowledge regarding the fundamental nature of reality itself. What does information truly mean in the context of the universe? The implications of resolving this paradox could change our understanding of everything from quantum mechanics to the very fabric of spacetime. As we continue to uncover the mysteries of black holes, the question remains, can we ever know what truly lies within? As we explore deeper into the universe's most enigmatic objects, we're left with a lingering thought: does the existence of black holes challenge the very nature of what we perceive as reality? As we move forward, the unfolding tale of black holes and information will reveal more about our universe and the cosmic dance of matter and energy. The debates rage on, but one thing is certain: black holes hold secrets that might unlock new realms of understanding. Black holes are not just cosmic vacuums. They play a pivotal role in the evolution of galaxies and the universe itself. Recent studies suggest that black holes, particularly supermassive black holes, are central not only to galaxies' formation but also to their structures and dynamics. Let's explore how these mysterious entities contribute to the grand tapestry of the cosmos. When a galaxy forms, it is essentially a swirling mass of gas, dust, and stars. Over time, under the influence of gravity, the matter coalesces to form stars and planets. However, the presence of a black hole in the nucleus of a galaxy helps to regulate the formation of stars. Research indicates that supermassive black holes can influence star formation by exerting gravitational forces that stabilize the galaxy's core. This process creates a delicate balance between star formation and gravitational pull, leading to the formation of stunning spiral galaxies, elliptical galaxies, and more. A prime example of this relationship is found in the Andromeda Galaxy. Located about 2.5 million light-years away, Andromeda's core houses a supermassive black hole known as M31*, with a mass approximately 100 million times that of our Sun. Astronomers have observed that the movements of stars around M31* reveal a profound gravitational influence, affecting the rate at which stars are formed in the surrounding regions. This interplay is critical. Without the gravitational pull of the central black hole, the galaxy could see an explosive rate of star formation, eventually leading to an unstable stellar environment. Additionally, black holes help to distribute heavy elements throughout the universe. During the life cycle of a black hole, as it collides with surrounding matter, massive amounts of energy are released, often leading to supernovae, explosive deaths of massive stars. These events scatter elements such as iron, gold, and platinum across the cosmos, providing the building blocks for new celestial bodies and systems. This cosmic recycling process highlights the symbiotic relationship between black holes and the universe's overall structure. As we observe black holes capturing and disintegrating massive stars, we witness a cosmic dance that speaks to the fundamental mechanics of creation and destruction. The idea that black holes can foster star formation might seem paradoxical at first. After all, they are known for consuming matter. Yet, understanding this relationship hints at the deeper mechanisms that govern cosmic evolution. As we venture deeper into the universe's secrets, we recognize that black holes may serve as the engines of cosmic evolution, shaping galaxies while also contributing to the birth of new stars and systems. In the grand scheme of cosmic evolution, black holes are not mere destroyers but vital architects of the universe. The journey of unraveling their mysteries reveals not just the dynamics of the cosmos, but also the very genesis of the stars that illuminate our night sky. This relationship between black holes and galaxy development is a testament to the intricate workings of the universe, a dance of gravitational forces, star formation, and cosmic balance. What other roles do black holes fulfill within this vast cosmic playground? To understand black holes, we must first comprehend how they are born. A black hole's genesis often begins with a massive star, one that is at least 3 times the mass of our Sun. When this star exhausts its nuclear fuel, gravity takes center stage. The star collapses under its own weight, creating a core that shrinks indefinitely while the outer layers of the star are expelled into space. This event is known as a supernova, and it is one of the most spectacular cosmic phenomena. Imagine witnessing a star's death from millions of light-years away. The explosion radiates energy, creating a brilliant flash that can outshine entire galaxies for a short time. It is estimated that supernovae occur roughly once every 50 years in a galaxy like ours. The energy released from such an event is astronomical, but what remains is even more intriguing. What happens next is a delicate balance of forces. The core of the star collapses into a singularity, a point where gravity becomes infinitely strong and the laws of physics as we know them cease to apply. This process is not only the birth of a black hole but also a cosmic reminder of the transient nature of stars. Once formed, black holes can also grow by accumulating mass from their surroundings. They attract nearby gas, dust, and even other stars with their immense gravitational pull. For instance, astronomers observed the formation of a black hole in the galaxy NGC 3603, which has grown by consuming material from its nearby environment. This growth contributes to the black hole's hunger, feeding it over time to reach colossal sizes. Supermassive black holes, often found at the centers of galaxies, can weigh billions of solar masses. This is a testament to their ability to consume matter, gaining mass over billions of years. Our own Milky Way hosts a supermassive black hole named Sagittarius A*, with a mass of about 4 million suns. The formation of these monstrous entities remains one of the great mysteries of modern astrophysics, challenging our understanding of gravity and matter in the universe. But how do we know these black holes exist? One way is through their influence on the stars surrounding them. Observations show stars orbiting an invisible point in space, leading astronomers to deduce the presence of a massive black hole. In recent years, telescopes like the Event Horizon Telescope have captured the shadow of a black hole, giving us a glimpse into this enigmatic process. Each advance we make in understanding black holes is akin to peeling away the layers of a cosmic onion. As we continue to explore, new stars are born, and others die, telling the story of our universe's complex life cycle. Yet the finality of a black hole's birth only leads to the next question: what happens to the information of the stars that fall into them? This leads us to the mysteries of Hawking radiation and the information paradox, themes that intertwine with our understanding of time and existence. How black holes form is just a piece of a much larger puzzle. Their presence impacts galaxies, star formation, and even the very fabric of time. As we ponder the continual cycle of stellar evolution, we come closer to understanding our place in the cosmos. What other secrets do these black holes hold? We may yet unlock the truth of the universe itself. In the vast expanses of the universe, black holes don't just exist in solitude, they often engage in cosmic dances, spiraling towards one another and, ultimately, merging. These events are not only spectacular but also serve as a significant source of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. The study of black hole mergers represents a revolutionary leap in astrophysics. The first direct detection of gravitational waves, announced by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, stemmed from the merger of two black holes. They collided approximately 1.3 billion years ago, and their merging created waves that traveled across the universe, reaching Earth just a century of years ago. For the first time, we had an audible connection to the distant cosmos. Imagine the scale of such a merger: two black holes, each several times the mass of our Sun, spiraling together in an intricate ballet of gravity, colliding in a violent embrace, and unleashing energy equivalent to that produced by all the stars in the universe combined for a brief moment. This energy is released primarily in the form of gravitational waves and is a remarkable confirmation of a century-old theory. But what can we learn from these extraordinary events? For one, they allow astronomers to test the predictions of general relativity in ways that were previously impossible. As black holes merge, their masses and spins can be measured, providing insight into the formation, evolution, and population of black holes in the universe. For example, the mass of merged black holes can reveal details about the progenitor stars and the environments in which these black holes formed. Studies have indicated that the properties of these mergers are telling us a lot about the cosmic history of black holes in our universe. Data from LIGO has shown that black hole mergers occur more frequently than previously thought, suggesting that many of these dark entities might lurk in the depths of the universe, silently waiting for their chance to collide. Additionally, researchers have detected mergers involving black holes of different masses, hinting at a diverse range of black hole formations across different environments in the cosmos. These mergers pose another question: what happens to the information that falls into black holes? The black hole information paradox, a cornerstone of theoretical physics, remains a tantalizing puzzle. It suggests that the information about the entities that fall into a black hole does not simply vanish but somehow is encoded in the black hole's event horizon. This has led to the formulation of various theories, including the holographic principle, which posits that all the information contained within a volume of space can be represented as a hologram on the boundary of that space. As we probe deeper into the understanding of these mergers, we find ourselves at the crossroads of modern physics. The quest for knowledge about black hole mergers not only expands our comprehension of black holes themselves but also challenges our notions of reality, time, and space. It compels us to consider the interconnectedness of the universe, where every event unfolds within the grand tapestry of cosmic history. The sound of merging black holes reverberates in the fabric of spacetime, inviting us to listen more closely to the secrets of the universe. The implications of this research stretch far beyond the black holes themselves and beckon us to delve into the heart of existence. As we continue to unearth the mysteries surrounding black holes and their interactions, we inch closer to enlightening the shadows of the unknown. What other enigmas lie hidden in the embrace of dark matter and cosmic phenomena? The journey has only just begun. As we step into the future of black hole research, we stand on the brink of a scientific revolution. The conundrums of black holes challenge our understanding of physics and the universe, but they also present incredible opportunities for discovery. The advancements in technology and observational techniques promise to take our inquiry deeper into the cosmos, unlocking secrets that have eluded us for centuries. One such advancement is the ongoing development of next-generation telescopes. The James Webb Space Telescope, launched in late 2021, offers unprecedented views of the universe. With its ability to observe infrared light, Webb is